Two ambitious missions for Japan. The SLIM lunar lander and the XRISM X-ray telescope flew into space. Japan has launched a mission intended to land on the lunar surface. The SLIM lander was designed to land within 100 meters of a predetermined target on the surface of the silver globe, rather than a few kilometers away as before. The same rocket also carried the XRISM telescope into orbit, which will look at objects emitting X-rays. The Japan Aerospace Exploration Agency (JAXA) announced the successful launch of the XRISM X-ray imaging and spectroscopy mission telescope and the SLIM smart lander for investigating Moon. 2. Explore the Moon. The launch took place at 1:42 a.m. Polish time from the Tanegashima Space Flight Center located on Tanegashima Island. The agency also reported that the XRISM observatory successfully separated from the launch vehicle about 14 minutes after launch, and SLIM after about 47 minutes. The flight was originally scheduled to take place 10 days ago, but was postponed due to unfavorable weather conditions. If all goes according to plan, SLIM will attempt Japan's first soft landing on the Moon in a few months. This is to be an extremely precise landing of the lander on the surface of our natural satellite, which will pave the way for even more ambitious feats, announced JAXA representatives. SLIM is intended to be the first of the lightweight probes to use precision landing technology, essential for future lunar probes. The project aims to reduce the mass of functional observation and landing equipment on resource-poor planets for future solar system exploration probes, JAXA officials wrote in the mission. Description: SLIM is only 2.4 meters high, 2.7 meters long and 1.7 meters wide. Its mass is about 700 kilograms, but nearly 70% this mass constitutes fuel. It will take a slightly more distant but more economical route to the Moon. It will reach the Moon's orbit in about 3 to 4 months. It will then observe the surface of the silver globe for about a month, after which it will attempt to land in the Scioli crater, a 300-meter wide impact facility located on the side of the Moon visible from Earth. The probe is scheduled to land within 100 meters of a previously designated point in the Scioli crater. The goal is to demonstrate precision landing technology that could open the way to landing and exploring other objects. By creating the SLIM lander, the goal was to make a qualitative change towards the ability to land where we want, and not where it is easy to land, as has been the case so far, JAXA representatives wrote in the mission description. SLIM carries 2 mini-probes that will be thrown onto the lunar surface after landing. According to the mission's press materials, These two small craft will help the mission team monitor the status of the larger lander, take photos of the landing site and provide an independent system for direct communication with Earth. Japan has already tried to land on the Moon. In late April, Tokyo-based Ispace's Hakuto R lander reached lunar orbit, a huge achievement for a private spacecraft, but crashed while attempting to land. So far, only 4 countries have landed on the Moon: the Soviet Union, Russia, the United States, China and, most recently, India. The second mission that was launched into space was XRISM. This is an X-ray observatory created in cooperation between JAXA, NASA and ESA. The telescope will explore the universe in high-energy X-ray light. X-ray astronomy allows us to study the most energetic phenomena in the universe, said Matteo Guainazzi, a scientist involved in the ESA project. This is the key to answering important questions in modern astrophysics: how the largest structures in the universe evolve, how the matter that ultimately composes us was distributed throughout space, and how galaxies are shaped by the massive black holes at their centers, he added. The observatory will focus particularly on the superhot gas surrounding galaxy clusters. JAXA designed XRISM to detect X-ray light from this gas to help astronomers measure the total mass of these systems. This will reveal information about the formation and evolution of the universe, ESA officials said in a statement. XRISM will not be the only X-ray telescope examining the sky from Earth orbit. Currently there are, among others, NASA's Chandra X-ray Observatory and ESA's XMM Newton telescope, both launched in 1999, and NASA's NuSTAR, which began operations in 2012.
Pas de soleil, pas de soleil, pas de soleil, pas de soleil.
Complex human embryo models created using stem cells. A team of Israeli scientists has created complete models of human embryos from stem cells. Scientists managed to grow them in the laboratory for 14 days. The embryo models had all the structures and cells characteristic of this stage of embryo development. This research aims to create a model that can help better understand a key moment in embryo development that affects the risk of miscarriage and the development of congenital defects. Similar models could also open up new avenues for research into infertility, drug testing, and tissue growth for transplantation. A team of researchers led by Professor Jacob Hanna from the Weizmann Institute of Science in Israel created complete models of human embryos from stem cells grown in the laboratory up to day 14. As reported in a paper published in the journal Nature, these synthetic models had all the structures typical of this stage of development, including the placenta, yolk sac, chorion and other tissues. Recently, similar models of embryos were created by scientists from the University of Cambridge and Caltech, but the models of Israeli scientists have a much more complex structure. Israeli scientists found that the models of their American and British colleagues did not contain several types of cells necessary for embryo development. Moreover, they did not have the structure characteristic of an embryo and did not show the dynamic ability to move to the next stage of development. The aim of the study is to shed light on a stage of embryo development called gastrulation, which occurs 2 to 3 weeks after fertilization. This is a critical stage of development, but scientists know little about it. The drama takes place in the first month. The remaining 8 months of pregnancy are mainly about intensive development, said Professor Jacob Hanna. But this first month is still largely a black box. Our stem cell-derived human embryo model offers an ethical and accessible way to look into this box. The model imitates the development of a real human embryo, especially the appearance of its incredibly beautiful architecture, he added. As in the work of researchers from Cambridge and Caltech, the models were created without the need to use sperm or egg cells, or even the uterus. Scientists have managed to coax human stem cells to organize themselves into synthetic embryo-like models. They used knowledge gained in previous studies on mice. They started by working with pluripotent stem cells, which have the potential to differentiate into many, but not all, cell types. Some of them came from adult skin cells that had been reverted to their pre-differentiation state. Others came from human stem cell lines that had been grown for years in the laboratory. The researchers then used a recently developed method by Hanna's team to reprogram pluripotent stem cells to revert them to an even earlier state, called the naive state, in which they are able to specialize into any cell type. This stage corresponds to the 7th day of the life of a natural human embryo, approximately at the time of implantation in the uterus. Hanna's team first began describing methods for generating naive human stem cells back in 2013, and over the years they have refined the methods that form the heart of the current project. The scientists divided the cells into 3 groups. The cells that would develop into the embryo were left unchanged. Cells in each of the remaining groups were treated with different chemicals to turn on specific genes, which would cause the cells to differentiate into one of 3 types of tissues needed to support the embryo: placental tissue, yolk sac, or chorion. Shortly after mixing under optimized, specially developed conditions, the cells formed clumps, about 1% of which self-organized into complete embryo-like structures. By definition, the embryo is self-directed. We don't have to tell him what to do. We just need to unleash its internally encoded potential. It is very important to initially mix the right cell types, which can only be obtained from naive stem cells and have no developmental limitations, Hannah said. The resulting embryo-like structures developed normally outside the uterus for 8 days, reaching a stage corresponding to 2 weeks of human embryonic development. This is the moment when natural embryos acquire internal structures that enable them to move on to the next stage, the development of progenitor cells. When the researchers compared the internal organization of stem cell-derived embryo models with illustrations and microscopic sections of anatomy in classic embryology atlases, they discovered an uncanny structural similarity between the models and natural human embryos at the corresponding stage. Each structure was in the right place, size and shape. Even the cells that produce the hormone used in pregnancy tests were present and active. Interestingly, when scientists used the secretion of these cells in a commercial pregnancy test, the result was positive. This means that the models faithfully imitated the process by which an early embryo gains all the structures needed to begin its transformation into a fetus. Many pregnancy failures occur in the first few weeks, often before a woman even realizes she is pregnant. This is also when many congenital defects occur, although they are usually discovered much later. Our models can be used to reveal biochemical and mechanical signals that ensure proper development at this early stage, Hannah emphasized. At a stage that corresponds to a week of gestation, the embryo models were aggregates of approximately 120 cells with a total diameter of approximately 0.01 millimeters. By day 14, they contained approximately 2,500 cells and measured 0.5 millimeters. By observing their models, the researchers discovered that if the embryo is not properly surrounded by the cells that make up the placenta on the 3rd day of the process, which corresponds to day 10 of natural embryonic development, its internal structures, such as the yolk sac, will not develop properly. The embryo is not static. It must have the right cells in the right organization and must be able to develop. Our complete embryo models will help researchers answer the most basic questions about the factors determining their proper development, Hannah noted. This ethical approach to unlocking the secrets of the first stages of embryonic development may open many research paths. It can help reveal the causes of many birth defects and infertility. It may also lead to new technologies for growing tissues and organs for transplantation. It may also provide a way to bypass experiments that cannot be performed on living embryos, for example, determining the effects of exposure to drugs or other substances on fetal development.